I welcome you, Professor, and the session is over to you.
Okay. Can you hear me? I'm not sure that the microphone is working. Can you hear me now? Okay, I think if you are 16 years old, what you should do is to, if you are interested in physics, is to learn as much as you can about physics in general, like classical physics, electromagnetism, and start learning a little bit about modern physics, because there are many things which can be interesting, and the important point is to find the kind of physics that you like, to have a passion for what you want to do. So I can enumerate a few fields in which a lot of fascinating discoveries remain to be made. Obviously, in astronomy and astrophysics, there is a lot of things that we don't know about. For instance, we now believe that there is a large fraction of the universe that we don't observe. It's called dark matter. It's a form of matter which does not interact with light, and that we have just a hint that it exists because of gravitational effect. So what is dark matter? How can we measure and detect it? It's a very great issue. Another issue is to learn more about gravitational waves, the origin of the universe, the connection between gravitation and quantum physics. So you have a lot of problems which are still open. But these are very big problems, big issues, which require a lot of knowledge and a lot of intuition. Nobody knows the solution to these problems. But you have also challenges in technology. We need to discover new forms of new energy sources, or to be able to exploit energy sources which do not have an effect on the environment as the fossil fuels have. So there is a lot of research in solar cells, in batteries, in new forms of energy. And in the domain of chemistry, there is also a lot of discoveries to be made. There is a chemistry which is good for the environment, that be able to do things without having to pollute too much the environment. There is a form of chemistry which is now being developed, trying to imitate what nature is doing with small amounts of energy, low temperatures. This is also a very interesting domain. Outside of physics and chemistry, there are fascinating issues about the brain. How does the brain work? A lot of things have to be discovered in neurobiology about the functioning of the brain. And you have, of course, all the research in computing science, about artificial intelligence. What you can do to in this area is also without any limits and boundaries. So really you have to choose what you like and what you want to do, and you have also to exploit all the possibilities which are offered to you, and very often the direction in which you will finally go will depend on the people that you will meet, on encounters, on luck, and you have to be able to recognize your luck when you have it. And so that's what you should be prepared. And to be prepared, the best thing you can do is to try to learn as much as you can when you are your age. So.
Okay, did you get the answer? Okay. So the next question is, it is rare that everyone meet their expected goals. What is the source of motivation that keeps you go on your way?
The motivation is curiosity and trying to meet the challenges that you have in front of you, and in the direction that you find interesting. In my case, as I have already said, when I started doing research, the laser was being developed, and I found this was a fascinating source of light, quite different from whatever existed before. And I decided I wanted to work in this area because I knew that there would be interesting things to do. And the motivation was that. and the motivation was also helped by the fact that many other people were working in the same direction. I could exchange with them. Was able to understand what they were doing, and this really helped for the motivation. So the point I would like to stress is that in the field of science and scientific research, you are not alone. You work in a big community which is worldwide. And this is really a privilege we have in this kind of career, in this profession, is that there are no boundaries, there are no frontiers. We work really at the global level. We always, now it is really, it has become a common thing to say that we are in a global market and that it's a global world, but it has been that in science for a very long time. Science has no boundaries, and you learn from a lot of people, and this is also a great motivation to go further.
Okay, the next question is, sir, from where does the universe get particles to form elements or matter in space?
This is a question about cosmology, about the origin of the universe, and I am not a specialist in this field, so I cannot answer precisely, but what happened is that at the beginning of the universe, the temperature, the energies involved were very, very much higher than they are now. The universe was much more dense than it is now, and there was no particles. There were only a situation in which all the interactions were merged into a single one. And when the temperature decreased, the universe got more and more diverse, and first the light and the particles separated at a given temperature, and then stars were formed, and during the nuclear reaction, the formation of stars, and when during the evolution of stars, the other elements were created by nuclear reactions. There are theories to explain that, and now we are starting to be able to test these theories by observation. For instance, about a few months ago, 5 months ago, the fusion of two neutron stars was observed by detecting gravitational waves, and this fusion was confirmed by observation of electromagnetic wave, light, and other radiation, and one has for the first time a glimpse of the way elements like gold were formed in the universe by nuclear reactions. So all this is a kind of machinery which depends upon the fundamental interaction in nature. Essentially, the nuclear forces are due to the strong and weak interactions, and the interplay between these strong and weak interactions leads to the creation of particles.
What if we use high-intensity laser in space? Will it interact with the particles in space?
You can, in fact, there are many projects which involve the use of lasers, eventually in satellites or in space. What the lasers can do is to measure with very high precision the distances. For instance, there's an experiment called lunar ranging, which was measuring the distance between the Earth and the Moon with a very high precision by sending beams to the Moon and looking at the reflection of the Moon of the light from the Moon surface using a corner cube, a mirror, which was deposited on the Moon by astronauts long ago. And for that, you need a very high intensity laser because you will collect only a few photons coming back. So that's one use of high intensity lasers for lunar ranging. And you may think of many other uses. There is a project called LISA to make a gravitational wave observation from outer space, having 3 satellites and look at gravitational wave which will slightly disturb the relative position of the satellites. And to measure this position with precision, you need lasers connecting the satellites in question. This project is a very long-term project which might take decades before being implemented in space. So there might be many uses for lasers in space exploration.
When we speak about light, photons come into account. Why? What is light exactly? Is it purely photons? Are they bright?
Are they what?
Are they bright?
Bright?
Are they shining bright?
Yes, yes. No, the photon is, okay, according to quantum theory, the photon is a quantum of light. Light is at the same time an electromagnetic field, that is a field which fills all the space, and at the same time is made of elementary particles called the photons. And these photons propagate at a very, like the light field, at the velocity of light by definition. They have no mass, their mass is zero, but they have energy. And they are purely quantum because these are, if you take a classical particle to have an energy must have a mass. A kinetic energy is proportional to the mass, whereas for a photon, even having zero mass, it has an energy because it has the speed of light. It cannot be described classically. It is a purely quantum particle. So it's very difficult to give a very simple explanation for that because it relies on quantum principles. So the best I can say is that the photon has a double aspect. It is the light has a double aspect. In some experiments, the particle aspect dominates and you see light as a bunch of particles. In other kind of experiment, it is the wave aspect which dominates and you see the light as a wave propagating through space. The wave in general represents the probability to find the particle. If the wave has a very small amplitude, it is not likely that you will find the photon there. If the wave has a large amplitude, if you make a measurement, you have a larger probability to find the photon there. And the same kind of ideas apply not only to photons and light, but also to particles. For instance, if you consider the electrons are also quantum particles, and they are the quantum of an electron field. It means that they have also a wave character. And if you want to find an electron at one place and you may put a detector, the probability to find the electron there will be proportional to the square of the amplitude of the electron wave, exactly like what I said for the photon. So this dual aspect, particle and wave aspect, is a general principle which applies in quantum physics to all kinds of particles and which is revealed most of the time at the microscopic scale, when you make measurement on single particle or you make very precise measurement at the microscopic scale.
Is photon the smallest quantity of light or is there a sub-photon also?
No, the photon is a quantum of light. But, yeah, but its energy is proportional to the frequency. So if you look at low frequencies, you can have photons with smaller and smaller energy and longer wavelengths. But the photon, you have no half a photon. The photon is a quantum of light, and you cannot divide the photon. For instance, if you put a beam splitter and you send a photon on a beam splitter, you will not split the photon in two. The photon will go half of the time one way and half of the time the other way. But it will only be one photon here or there.
Are we ever going to understand quantum physics?
Are we
Ever going to understand quantum physics?
Are we going to understand quantum physics?
He found it difficult,
No,
it seems.
it depends what you call by understand. Okay, there is a quotation by the famous physicist Richard Feynman used to say, "Nobody understands quantum physics." And Niels Bohr said, if you think that quantum physics is not strange, it means that you have not understood it. So you see there are this kind of paradoxical statements about quantum physics. What does it mean? It means that the world that we see around us appears classical. For instance, you never see a particle going through two slits at once. It goes either through one slit or the other. You never see a cat which is at the same time dead and alive. It is either dead or alive. So you see a world which appears classical, and our brains are used to think in these terms. And even our vocabulary, even the words that we use when we speak, have been formed to describe the classical world. So the first time people have realized that at the microscopic level, things did not behave that way, they were really surprised and even shocked. Einstein was really shocked by the quantum theory, and he, all his life, he thought that one day one would go beyond these quantum principles and retrieve a classical world. And he tried to do that, and he even, after Einstein's work, even some experiments were suggested to try to prove quantum physics wrong. And all these experiments have failed to prove that quantum physics was wrong. They have all confirmed that the strangeness of quantum physics was there and would stay there, at least from all what we think. So I think we have to get used to that. And there is one vocabulary which you can use and which will not betray you. It's the vocabulary of mathematics. In fact, if you use maths, quantum physics is very simple. The kind of mathematics that we need for quantum physics, at least to understand the principles, is just linear algebra and simple mathematics, which consists in combining vectors, something that you can do even at the end of high school. So if you put quantum physics in mathematical terms, there is no problem. But of course, the problem is that we are not used to think all the time in mathematical terms. What I used to say is that our brains have been formed by the Darwinian evolution over thousands of generations to adapt to the world that we see around us. For instance, if you are thrown a stone at, you know that the stone will follow a parabolic trajectory and that you better avoid it if you don't want to be hurt. And the people who have been able to understand how the stone will fall will have a better chance of surviving. And so after many, many generations, we got this into our brains. And we have no reason to understand quantum physics, at least in the general world, because we never see a stone going into two directions at once, interference effect. So we don't have the intuition of that because our brain have not been formed for this intuition. So maybe in thousands of generations, if quantum physics becomes very, very used in very, very many devices and experiments display quantum physics clearly, maybe our brain will learn how to cope with it and it will appear less strange, but I am not sure.
Yes, sir. What is dark matter?
Dark matter? This is not my field, this is cosmology, but what I know about dark matter is that astronomers have been measuring with high precision the motion of galaxies and trying to explain the motion and the rotation of galaxies in particular using Newton laws or Einstein laws of general relativity. And they have found that in order to understand this motion, and if you take into account only the known matter, the matter that you can see, the galaxies and the stars that you can see, there is something which cannot be explained. Apparently, there is a huge mass, much bigger than the mass of the known matter, which interacts in a gravitational way with the galaxies and which is needed to explain what we see. So there are two possible explanations. Either there is a dark matter. Why we call it dark? It's dark because you don't see it. It means that it doesn't interact with light. Either that, or we have to modify the gravitational laws, Newton and Einstein general relativity. But from what I heard, physicists and theorists are less keen to give up gravitational laws because they have been tested in many ways. And the general opinion now is that there is this dark matter somewhere. And there are different ways to look for it, either by astronomical measurements, trying to find some evidence, or in the laboratory, if one can produce dark matter or detect dark matter in accelerators or in machines which are man-made. And there are different theories going beyond what we know presently, which try to introduce these ideas of dark matter into physics. But for the time being, it's very, very open, and there is no answer to that question. So what is dark matter? We don't know. We know it's very difficult to find because if it interacts with light, it interacts very, very weakly with light. And it's one of the big mysteries of today. You know, at the end of the 19th century, about 1.5 centuries ago, the big mystery was ether. According to Maxwell, the electromagnetic waves, light was an electromagnetic wave, but a wave, up to that time, a wave it was a motion of something. And the something which was moving, according to physicists in the 19th century, was a mysterious medium called the ether. And the ether had very strange properties because the ether was in space, but it also was inside water, inside the transparent media, because light could propagate through this media. So they tried to imagine a medium which would be carrying light. And after that, when Michelson did his experiment, and then when Einstein developed the theory of relativity, it was found that the ether did not exist at all, and that we did not need the ether to understand phenomena. So maybe now we think that there is dark matter, and maybe there will be another explanation. We don't know. This is a domain which is completely open for science.
Yeah, sir.
Yes, it's possible. I don't know. Maybe there are some region of space where there is more dark matter than others, but I don't know.
Go to the next.
This motion is known. The tides are due to the motion of planets around the moon. When the moon is rotating around the Earth, not only the moon is rotating, but it has also a gravitational effect on the Earth, and this explains the tides. The fact that twice a day the Earth's surface and the water are pushed towards or against the moon. So there are tidal effects which are due to the fact that the planets are not completely rigid, and there is a way of there is a small stretching effect due to that. So I think what you're talking about is related to tides, to the moon.
Moon is getting pulled towards Earth. Moon is getting pushed away with centrifugal force.
Yeah, the moon is pushed toward the Earth by the gravitational force, and it stays on orbit because it has a tangential velocity. So it's, in fact, if there were no gravitational force, the moon would go in a straight line. And in fact, the circle is it's a way of falling without falling, because it goes on straight line, and then it is slightly pushed toward the Earth, so it follows a circle instead of going on a straight line.
Good. But moon is also
No.
to be pushed away by the centrifugal
No, the centrifugal force is not a real force. Centrifugal force is an inertial force in the frame, in the rotating frame itself. So it's not a physical force. The physical force is a gravitational force, and one way to explain the fact that the moon does not fall is to go into its frame and to say that this force is compensated by the inertial force that you're talking about. But these are forces of different nature.
Yeah, the student that is like.
So I guess I answered to that question. The question is, what is the medium in which light is a wave? And there is no medium. The light is just electrical magnetic field exists in vacuum, and they propagate in vacuum. You don't need a medium to propagate the electromagnetic field. So this is part to understand that in depth you have to do special special relativity. And the point is that the strange thing about light is that its velocity does not depend upon the observer. If you suppose that you have a light beam going away from you and that you try to run in the direction of the light beam, let's say go in a rocket which goes very, very fast, and you want to try to catch the light beam, to go as fast as the light beam, you will never be able to do it, because whatever your velocity, the light will always be at 300,000 kilometers with respect to you. And this is the starting point. I think one says that this was the starting point of the special theory of relativity. The young Einstein, when he was a child, asked himself the question, what would happen if I were able to catch a light beam? The light beam is oscillating, so it's an electromagnetic wave which is oscillating. But if you are able to ride the crest of a light beam, it does not oscillate anymore. You are at the top of this light and you follow this. So then what Einstein thought that it will no longer be an electromagnetic oscillating field, it will be a static field, because I will be going as fast as it is. If it is a static field, and if I try to apply Maxwell's equation, then there is something which doesn't work. So Einstein understood that there was a lack of consistency between Maxwell's equation and the possibility to catch up light. And from then, he developed the theory of relativity, which does not need any medium for the light to propagate through. So you have to think about that, and I cannot explain it in a few words, but this is really the heart of the special relativity theory.
Yes, next, what's the difference between a magnet and gravity? What particles make difference in attracting?
What can you show?
What is the difference between magnet and gravity?
Electromagnetism and gravity?
No, magnet and gravity.
Magnets?
Yeah, magnet. Magnetism.
Yeah, no, the magnetic force is...
And what particles make difference in attracting?
No, the magnetic field is an expression of the electromagnetic, it's a part of electromagnetic theory. The fact that you have magnets, or that a circulating current corresponds to a magnetic moment, this is explained by Maxwell's equation. And this force, the force between magnets, or the force, is mediated by photons. In the theory of electromagnetism, particles interact with each other by exchanging photons. In the case of gravitation, it is supposed that the masses, if there is a theory of quantum gravity, the gravitational force is mediated by particles called gravitons, which are the quanta of the gravitational field. But these gravitons have not been observed, of course, and in fact we don't know exactly what they are, because there is yet not a consistent theory, quantum theory of gravitation. And the difference is that electromagnetic forces depend on charged particles, and gravitation is not related to charged particles. It's only related to the mass, and it's a much, much, much weaker force than gravitation. If you look, for instance, if you take a hydrogen atom, proton and electron, the force between them is an electromagnetic force. But also, there is also a small gravitational force, because the proton has a mass and the electron has a mass. But the gravitational force is 42 orders of magnitude smaller than the electromagnetic force. So the gravitational effects in atomic physics are completely negligible. The only time when you have a gravitational effect is that if you take an atom, put it to rest, then it will be submitted to the attraction from the Earth. So one has observed gravitational force between atoms and the Earth, but never between two atoms, because two atoms have a much, much too small mass to feel this force.
How scientists calculated the speed of light? How scientists calculated speed of light?
The speed of light.
Yes.
Okay, I think I discussed that in the last meeting. Yeah. There are two ways. First of all, how was the speed of light measured, and then how it was calculated. How it was measured, it's a very long story. It started in the 16th century by attempts by Galileo. Galileo tried very simply to uncover a light and had an assistant several kilometers away. And when the assistant saw the light, he uncovered his own light, so Galileo saw the reflection. And of course, it was quite instantaneous because the time it takes for the light to propagate through a few kilometers is microsecond, so there's so nothing. In the same way, if you put a mirror 10 kilometers away and shine a laser beam, you will not see it because your mind is not able to see the difference between short time intervals. But now, if you have a detector, a fast detector, and if you do that, you will see the time it takes for the light to go back and forth. And in fact, laser ranging is used every day by geometers, people who, for example, if you want to measure the size of this room, there is a laser point.